Hello, and welcome to the Introduction to Line in Space. In your previous math courses, you have learned how to represent a line in the two-dimensional coordinate system, where typically the construction of the equation requires a point on the line and the slope of the same. A similar requirement holds for quantifying a line in more general dimensional settings, especially the 3D coordinate system. The main difference is that instead of slope, we need a vector, let's say v, which is parallel and describes the direction of the line. To represent an arbitrary line in such coordinate systems, we also need a point on the line, say the point P, which can be represented as the position vector OP, which we name R sub 0, where O is the origins of the coordinate system. To quantify an arbitrary point on the line, say the point Q, in terms of P and vector V, we observe using the triangle law that vector OQ equals to R sub 0 plus PQ. And since vector PQ is parallel to the direction of vector V, we can write PQ as a scalar multiple of V, namely, let's say, T times V, where T is a scalar which depends on the position of Q. Here you can see that as T varies through all the real numbers, the tip of PQ traces the whole line. Here we can represent the line via the vector equation R equal to R sub 0 plus T times V. Also, from your algebra and pre-calculus courses, you have learned that two arbitrary lines in two-dimensional setting can either be parallel or intersecting. Well, the situation is a bit more interesting in 3D. So in 3D, given two arbitrary distinct lines, they can intersect, which means they have a common point. They can also be parallel, meaning they have the same direction vectors but no common point. The extra and special situation is that these two lines can also be skew, where they are not parallel and not intersecting. In class, we'll show you techniques for detecting this relationship between the two lines. An important problem which arises often in application is finding the distance between a point, say A, and a line whose direction vector is V. To accomplish the task, we first pick an arbitrary point B on the line and move the vector V so that its initial point coincides with B. We recall that the magnitude of cross product BA cross V is the same as the area of the parallelogram spanned by these two vectors. Also recall that the area of a parallelogram is its height times its base length, which in this situation equals to the product of the magnitude of V and the distance which we are looking for. Hence, the distance in question is simply the magnitude of the cross product here divided by the magnitude of the direction vector. In summary, we have just learned that in order to successfully represent a line in space, we need a point on the line and also a vector parallel to and showing the direction of the line. We have also learned that between two lines in space, they can either be intersecting, parallel, or skew. And lastly, we have been introduced to a technique for finding the distance between a point and a line.